This video will cover the Big Bang Law. It's in a series of 3 videos that I would suggest you view together. The Big Bang Law, secondly, Einstein's relativity law, and third, the cosmic clock. These first 2 are presented so that you'll be able to understand the cosmic clock, which is a very important concept to be understood. Now, the Big Bang Law is something that was initially given a derisive name, Big Bang, by someone who didn't believe it. That name stuck, and it has over time developed not into a theoretical science, but now is a science, and it is the Big Bang Law, not the Big Bang Theory. And it basically is that the universe began as a small dot. Everything in the universe was in a small dot, and it basically blew up. Now, I hope you have viewed the scientific method video so that you have a remembrance at least that there are 5 steps to the scientific method, and I'll show you the first 4 here for the Big Bang Theory. Initially, it was observed that the universe was not static. This was a startling discovery, and it was startling because up to that point everyone believed, as Isaac Newton believed, that the universe was static. It was just kind of a mosaic picture to look at, and it was just sitting there, and we were on the earth just viewing this static, unchanging, more or less unchanging background picture. Well, it was discovered that instead some galaxies are moving away from each other at very high velocities. And so this was the initial observation that was made. A theory was developed, and it took a little bit of thinking and playing with physics that the theory said that all matter and energy was initially confined to a very small region, which was very high density, very high temperature, and then it exploded apart. That basically came because if the universe was observed to be expanding now, in the past, it's logical that it must have been smaller and smaller and smaller and smaller, and that leads you to this dot idea where everything was combined to a very small dot. Subsequent information that came about was that astronomers are able to detect not only stars in our own galaxy, the Milky Way galaxy, but they're also able to detect other galaxies from amongst the celestial objects that they can view, and they discovered that galaxies are moving away from each other at very high speeds. So this was the initial 3 steps of the scientific method, where an observation was made, a theory was developed, and more or less the data seemed to pretty well agree with it. Well, as with all theoretical sciences, one needs to make predictions as to what should be a result of the theory that you've developed. And here are the 2 major predictions for the Big Bang Theory. One is there should be some radiation left over after the Big Bang, that not all the energy was converted into matter. There was a huge quantity of matter that was all at high temperature and high density, or I should say not matter, but quarks that were initially, we'll see in a second, highly energetic particles that were all together. And when this cooled down, some of that energy was converted to matter, but there was energy left over. So there should be the discovery of some background radiation that was due to the Big Bang. And if it's found, it has to have little special characteristics. It can't just be a uniform radiation signal coming uniformly from every direction. It needs to be slightly non-uniform. And that gets a little bit into the details of the Big Bang Theory, but basically, if it were uniform, then there would be no suns and stars and no galaxies. Everything would be just a uniform distribution of mass throughout the entire universe, and there would be no life, no detailed phenomena within that uniform mass. And so there had to be a little bit non-uniform. So here is basically a pictorial view of what I just said. Here is that big dot, or a small dot, many times bigger than it actually probably was, shown on this slide. But here is this dot, and all energy and everything from the universe is in that small region. Just absolutely everything is there. Now, its initial temperature was in excess of tens of trillions of degrees. I'll show you in a minute why we know that it was over 10 trillion degrees, probably 20, 30, 40, 50, who knows. Very, very, very high temperature. And all of that matter was in the form of something called quarks. These are fundamental particles, highly energetic particles, building blocks of nature, and it's believed that everything was in the form of quarks before the Big Bang. Now, in order for that bang to have happened, it is now known, and this was a modification of the initial Big Bang theory, it is now believed that there had to be a rather significant expansion of that dot before the ignition of the explosion. So there was a region of great expansion of the universe. It was greatly expanded from that infinitesimally small dot, and then shortly thereafter, the millionth of a second, very shortly thereafter, there was something called a homogeneous explosion, where everything flies apart from everything else. This differs a bit from what you perhaps have seen or experienced. An explosion of a firecracker is just something that happens at a point. Explosion even of a nuclear bomb is something that happens at a point and just radiates out. Well, a homogeneous explosion is something where everything explodes in every location. You'll see that in a second. So what has happened here is the universe has expanded even beyond its initial expansion, and now these arrows in here going in all these various directions are meant to imply that everything is flying away from everything else. And based upon a linear accelerator experiments that we've done here on Earth with quarks, we know that when the temperature gets to 10.9 trillion degrees, 10.9 trillion degrees, super high temperature, that is the point that the physicists call quark confinement. That is the point at which all the quarks that are going to convert over to mass, matter as we know it. And so at that temperature, all the mass that's ever going to be formed is formed, and as the universe expands further and cools below that temperature, no more mass can be found. No more mass can be formed at all. And the remaining quarks in the form of energy that's left over is going to be radiated as cosmic radiation, as radiation that's going to come from the explosion of the Big Bang. Now in 1959, that cosmic background radiation was discovered, and it resulted in the 1978 Nobel Prize for Physics. And it was one of those discoveries that was made by a couple of IBM scientists who were setting up a large antenna to look for radio signals from space, not visible signals like astronomers do, but radio signals. And as they were setting it up, they had a great difficulty in eliminating a small quantity of noise to their radio telescope. And they tried everything that they could think of, shutting down nearby freeways and I think even a power plant for a while, and did things when days when things were quiet on weekends, so there wasn't all kinds of traffic around. They never were able to eliminate that noise, and ultimately that noise was discovered to be a remnant of this cosmic background radiation. So here is the summary of the science as we know it for the cosmic of the Big Bang theory, and you know that these three initial correlations were presented. These were the two predictions, and the first prediction was shown true in 1959 when the cosmic background radiation was discovered. It was a prediction from the Big Bang theory that came true. There was a second prediction that also came true a little bit later in 1989 when NASA sent up the COBE satellite, and this satellite's mission was to look for this non-uniform directional behavior of this cosmic background radiation. It is very slight, but they did measure it, and it therefore is a further proof that the Big Bang theory is now the Big Bang law. In summary, the Big Bang theory is the Big Bang law, and detailed observations of that remnant of the background radiation prove the theory to be correct that you've just seen. So it is a law, it is no longer a theory.